Okay, we're going to start talking about the radiative heat transfer between two or more surfaces. Basically, from last time, we know that the surface, if it radiates the energy out, it's going to be a combination of emission and also reflection. In the words, we call it radiosity. Okay, so let me make a note over here. This is the radiosity. Uh, Before we go deep into detail, let me remind you once again that radiation is the surface phenomena. Okay, and if any surfaces has the temperature over 0 degree Kelvin, it always emits the energy out. It's not just only the subject of interest, but if you talk about the other subjects or the surrounding, if they are the subject and surrounding, they all have the temperature, they all have temperature over 0 degree Kelvin, they too are gonna emit the energy out. And those kind of energy gonna arrive to the object of interest. So if we have a system, they emit the energy out in terms of radiosity, they also accept the energy in. In order to provide the equilibrium condition, energy balance on the system or the object of interest should be considered. And we would like to say how much of the surface of interest gain or lose its energy. And the energy balance equation needs to be established. And on the condition that the medium in between the objects and also the surrounding should be non-participating. Okay? Surface can emit or deflect energy out in terms of radiosity. So if you take a look at the concept of radiosity, if you have a surface of interest, let's take a look at the picture on the left-hand side. It's emit the energy out, and also the reflection, the green one, it is the radiosity. If the surrounding enclose the surface itself, all of the green energy can arrive to the surrounding, meaning that the percentage of energy leaving the surface onto the surrounding would be 100%. If you talk about the system, on the other hand, on the right hand side, the system emit the energy, the radiate the energy out, and you have another surface, which is the in your interest too. If the first one emit the energy out, basically previously it's arrived 100% to the surrounding. Right now there are another surface blocking the direction, some part of the direction of the radiation. It's gonna accept some of the radiation away from the surrounding. So there will be percentage of energy from the surface one arriving to surface two. We would like to find how much is it, how much the radiation will reach to another surface will depending on how much that surface is exposed, what is location of the second surface, or what is the temperature of the surface too. We will define another terminology. We're going to define the quantity which describe the ratio comparing the amount of heat radiation from surface I reaching to surface J in comparison with the total amount of heat radiation leaving the surface. We're going to give you the new terminology, which is Fij, and we call it view factor. Okay, so we will go to the next slide. By having that in mind, view factor is defining as some ratio, but the ratio is specified by heat radiation leaving surface I and reaching, this is reaching to surface J, okay, over the total amount of heat radiation leaving the surface I, Qi. Okay, so we will represent the Fij by quantifying this to be Qi right direction to J. Okay, Qij specifying as the Q which leaving surface I reaching to the surface J. The total heat radiation leaving the surface at this point, it is the Aiji. This is wrong. We're not going to talk about the Qi yet. Okay, and then the substitute the Qi to J and Aiji into the Fij, we got this equation. If I rewrite this equation once again, we know that the Qij is going to be equal to Aiji Fij. Okay, meaning that you can find the amount of Qi to J, which is which will answer my previous question. How much the energy leaving surface I and reaching to surface J? Right now, we can find Qij directly from this equation, providing that you know Ai, Ji, and Fij. Okay, so how do we find the Qij mathematically? Well, you define the radiation mathematics. If you have the area of Ai and you have the area of Aj, okay, and we're talking about the small part of the Ai, which is Di Ai, and we're talking about the small part of Aj, which is Daj. And there's the line connecting the two together, and it's specified by the distance r. And we have the axis, the normal axis to the surface. Okay, this is the normal axis to the surface, and we're going to define the theta, which is the angle between the normal surface and also the connecting line r. So we're going to have the theta I and we're going to have the theta j. In mathematics, we can find the dqi to j equal to the intensity from the I. This is the intensity of the radiation multiplied by cosine theta I, dai, d omega j to I. What is the omega j to I is the solid angle. Let me remind you again, this is the 3D angle. We're covering this a little bit previously on the previous session. And we know that the solid angle is specified have a relation with the theta I and AJ and also the R square, something like that. So we can substitute the component into this, okay, into this equation, and this is what we have. Providing that we know that the radiosity I e plus r equal to j over pi, and I e plus r is something like that. We substitute that into that. So this is the element of the heat transfer, leaving surface I to the surface J in terms of radiation. And if, but this is elemental value. So you need the total value. Total value is trying to indicate all the heat transfer in every element. That's why you come up with the double integral like that. So basically, this is just a map. Okay, you can skip this part, or you can study by yourself in the book. Okay, but if you ask me which one is the most important part, this equation. Okay, just take a look at this equation once again, and you can see that we can substitute this into that. Okay. So if I substitute that qi to j with this equation, okay, and after plugging in and rearrange the equation once more, you're going to have the fij. Okay, so this one allow you to use math to solve for fij. Why fij is important? Let's say, take a look at this equation. This is the why the fij is important. Okay, take a look at this equation. So if you know fij, you can find the qij. That's what our intention is. Well, mathematically, you use this equation, but we are fortunate enough to have the previous work has been done by the others, and Fij can be found from closed form equation or graphical representation. And this is below in the table 13.1. I took it from the Incompleted book. You will see that there is a situation where you have the surface. This is just the example. And this surface is called surface J. And you have this surface called surface I, okay? And this surface emit the energy out. We would like to know how much the energy reaching to from the surface I reaching to the surface J. And this is the equation. There will be a number of terms like the W1, W2. It's just a bunch of the dimension of the problem itself. So it has the parallel plate case. It has the inclined parallel plate case. We have the perpendicular plate. We have the three-side enclosure, which I think this is important. In the most of the final exam in the previous year, they used this one, okay? Meaning that they're going to be three surfaces involved in the analysis. We have the parallel cylinder. We have cylinder 1, cylinder 2, and this is called I, one called I, the second one is called J, and this is the equation for it. Cylinder and parallel the rectangle. Okay, this is the plate. We call it I, and this is J. J is the cylinder. Okay, so and we have a surface of the row of cylinder. We have cylinder 1, 2, 3, 4, 5, 6, and we have the the parallel plate. How much the I radiate to J, because each of the cylinder it emit the energy out. Okay, so this is the for drying process application. Okay, the example go through additional table, but this is in 3D. The previous table is for 3D 2D problem. This is for the parallel plate on the top of each other, and the coaxial parallel this one, and together with the perpendicular rectangle. Okay, this one. And you can see that for perpendicular rectangle, the way you calculate the Fij is very complex. Okay, imagine that you have to punch the number in calculator in responsive to the term on the right hand side. That would be taking too much time for you to put a number on. So if you don't like it, be sure that you have the graphic representation, meaning that you don't have to punch in the number, you just read it from the graph, providing that z, y, x dimension of the plate, and you can find the z over x, and you can find y over x, and you can select the line that you have responsive to the number y over x, and read the z over x over that line, and then you're going to have the Fij approximately. There will be some error from your reading, but that's fine. Okay, be sure to take a look at this graphic representation instead of going directly to the closed form expression. You might end up spend too much time punching the number in the closed form expression. So this is another example of the parallel plate on the top of each other, or the coaxial disc, meaning the disc on the top and the disc on the bottom. It share the connection between the center line and the plane of the two discs in parallel. Okay. So once again, if you want to find Qi to J, which is AI, Ji, and Fij. Now, by having this graphic representation and also closed form solution, you know Fij. All you have to do is to find J and multiply by I, okay? And then you're gonna get this one. The problem is still there, okay? How much Ji, okay? So later, okay? There is another way to find the Fij. We call it the cross-string method, okay? And it's available in the book of Senjo. And the picture and everything and the example, I took it from the older book, the Bayashi Toku, and also the Osisek book. This is the quite old book, but I give you as a reference anyway. You want to browse it out. And this is cross-string method is trying to find the view factor for 2D enclosure. When I say 2D enclosure, you're going to have the surface, for example, on the right hand side. Actually, you have just only two surfaces. Okay, surface 1 and surface 2. However, the surface 1 and surface 2 can we can think of them as the enclosure 2, in spite of the fact that it has just only two surfaces. When it has just only two surfaces standing apart like that, how do you make a decision that it is the enclosure? Well, if you think of it, we don't have no surface on this side, and we have no surface on this side too. If you have no surface on this side, it's going to be, let's say, it's still, if there is no surface on this side, it's still a surface of surrounding. If no is surface on this side, we still think of it as the surface of surrounding. What does it mean? What did it mean by that? Let's take a look. Let me clean this thing out first. If we have a surface area 1 like that, and the area 2 like that, and I say this is enclosure, you might ask, how on earth that it can form the enclosure? It's not enclosure at all. It's just the two surfaces standing apart. Well, if I add imaginary surface over here, this is surface of the surrounding. This is surface of surrounding. Okay, so by having the red surfaces and green surfaces, combine them together, there you go. You have the enclosure right there. When you have the enclosure, the cross-string method can be applied in order to find the view factor. Okay, let me erase this and go back to this one. Okay, well, how do you find it? Okay, once again, you have a surface 1, your surface of interest, and you have a surface 3. This is also your surface of interest. You want to find the Fij. Let's assume that there is a 2 surface, which is real surface. This is surface 2. Okay, this is surface 4. It's not the surrounding anymore. Let's say it is surface. You want to find the Fij, which is right now F13. Okay, how do you find it? Well, you have to find L first. Okay, you have to find L1, L2, L3, and L4. What's this L1 and L2? L3 and L4, you might ask. Okay, let me find the blue one. L1, it is the L. What is the L? L is the length of the surface. Okay, if the surface is flat or concave. For example, if surface 1 is flat, the length L would be this one. Okay, if surface 1 is concave like that, the length of surface 1, L1 is something like that. Okay, so it can apply to A2, it can apply to A3, it can apply to A4, and it can apply to any other surfaces. Okay, but if it is the convex surface, what happened? If convex surface like that, this is A1, well, it is the conforming length, L1, okay? So it's gonna be conforming length if the surface is convex, okay? So in this case, we can find the L1 to L4. So L1 is something like that because it is the concave, okay? L3 is something like that. L2 is something like that because they are all concave surface. However, the convex surface is on the surface 4. So this is the L4. Okay, so L1 to L4 are the length of the surfaces. However, L5 and L6 are the diagonal length of the enclosure. So this is the diagonal length, L5 and L6. Okay, so what is the cross-string method? Cross-string method is this equation. Okay, if you want to find the F13, you multiply the F13 by L1 is equal to the summation of diagonal line. Okay, and this is the length of the surface L2 and L4. This is the length in between, meaning that we're going to use a green one. The first bracket is summation of this line, diagonal line. L2 and L4 is the connecting line. Okay, so that's the concept. Okay. Then I'm going to give you the example. Example would be, this is the area 1. Okay, this is the area 2. Okay, and you want to find the F12. So F12 is the summation of diagonal line. This is diagonal line, L5, L6. Minus the connecting line, L4 and L2. L2 and L4 over 2. Okay? So now the game is that you have to find L5, L6. Oh, I'm sorry, this is going to be L1. Okay? And you have to find the L2 and you have to find the L4. Get it? And then L5. What's the L5 once again? L5, let me say, use the red one, L5. L5 is the L5 equal to L6, right? It's because of the symmetry. And you want to find this one. Okay? And this is because L5 is equal to L6. You know that this is B. And you know that this is C. Okay? So this is also B. And take a look at this triangle. This triangle, the length on this side is the is 2C. Okay. And the on the over here is the length D. Okay, so you have the triangle like that. To C, and this is D. Okay, how do you find the length over here? This is L6. Okay, so take a look at this, the triangle. The angle is this 90-degree. So you can use the Pythagoras. And well, how much is this blue one? This blue one is going to be, let me say, this. How much is it? Okay, so this is, because this is C, and this one is C minus, this is B, right? So this one is going to be C plus B. Okay, so L6 square is going to be equal to D square plus C plus B square. Okay, and once again, I delete this thing out. Okay, and then we would like to get L2. Where's the L2 again? L2 is over here, right? And the same thing, we take a look at this, the triangle. Because this is length of D, how much this is thing? This thing is C minus B. Okay, so L2 gonna be, L2 square is gonna be D square plus C minus B squared. So I know L2, I know L6. I know that L5 is equal to L6 is 2 L6, and this is 2L2. Okay, so 2 got cancelled out, and F12 equal to L6 minus L2 over L1. Okay, what is the L1 again? L1 is here. L1 is here. Okay, so L1 is B. So I substitute B inside here, and I substitute L6, L6 square over here, right? And I substitute L2 over here. This is what I'm gonna have. There you go. You have yourself the F12. So this is an example of what's going on by using the cross-string method to find the Fij. Okay. Let me clean it up a little bit here. Okay, we move to the next step. Well, it seems that we have to deal with surfaces, meaning many of them inside the enclosure. And if you want to find the Qij, heat leaving surface I to first surface J, any I or any J in the enclosure, you have to deal with Fij. So you need to find so many Fij. For example, if you have 3 surfaces, it's going to be F1, 3 surface, something like this. Okay, surface 1, surface 2, and surface 3. And they are all have radiation inside. Okay, so you have to find the F11, F12, F13, F21, F22, F23, F31, F32, F33. 9 of them. Can you find 9 of them? Well, sometimes yes, it wouldn't hurt, and it's require you just only your time. to take a look at the table, to take a look at the example, the expression that you have. Remember the previous slide, the table that we have, expression, the big equation that we have, right? So, but you have to find it 9 times. So sometimes it's very inconvenient to do so. Is there any way that we can find the Fij easily? Supposedly, you can find it in a very simple way. The answer is yes. You don't have to always go to the table or the expression every time. You can use what's so-called the view factor relationship, okay? The first relationship that I would like to talk about is reciprocating relation. Take a look at Fij, okay? Fij giving you this equation. That's why I said this equation is important, okay? How about if you want to find Fji? Fji is just switching between I to j and j to I. So I just substitute what previously is I with j and what is previously j with I. And I got this equation, okay? But, you know, this indication and this indication are practically equal. In spite of the fact that this is the integral of ai first and then integral of aij, and this is the integral of j first and then I, but it can switch, okay? The order of integration can be switched, and such that we can write this equation switching the order. Fji going to be equal to aj, the same, and then the integral, I just switch it back, okay? Before, this is j first and then I, so I'm switching I and j later on. That's fine. It's still equal. So I take a look at these 2 equations then. This equation and that equation, okay? This one are equal. So this one is the Mrs. Smiley. Mrs. Smiley going to be equal to Fi Ai Fij. Mrs. Smiley going to be equal to Aj Fji. So this one are equal. So I make the conclusion that Ai Fij going to be equal to Aj Fji. Right? So we call this thing reciprocity relation. Okay? So how we can help? Because if you can find Fij from the table or from expression, what do I mean by that? Well, remember, you can use this graph like that, this graph, or this equation. Okay, you can even use the cross-string method. If you find the Fij, you can find Fji right away from the fact that Fji going to be equal to Ai Fij over Aj right away. So meaning once you can find F12, you can find F21 right away. If you can find the F31, you can find, if you found the F31, you could find the F13 right away by using the reciprocity relationship. So in this case, you need the 9 view factor. You don't have to go to the table or the plot or the expression cross-string method 9 times. No, you probably deal with it just only 4 or 5. Okay, and the rest you can use the reciprocity relationship. Okay.